Hello. Hello.
or help.
Good afternoon, everyone. We
Good
will
afternoon,
wait.
ma'am.
We will wait some minutes and then we will start.
Okay, ma'am.
Yeah. Good morning, Professor Sabrina.
Good morning.
Yeah. We'll wait for 2-3 minutes, then we'll start.
Sure.
Okay. Okay. Hello, Professor Sabrina. Shall we start?
Sure. Let me share the screen.
Sure.
There it is.
Yes, it is visible now.
Can you see it?
Yes, we can see it.
Perfect. So, good afternoon, everyone, again. And today we will first finish this lecture on passive radars, and then we will move to MIMO systems. So let's see some example of real passive systems that have been designed and implemented in some country. Of course, this list cannot be exhaustive, so complete. There are many other systems also developed by university department, because I mean, having a small passive system is much easier and much less costly than having a active system. And there is another characteristic. Passive systems, as we have seen, do not transmit any waveform, so they don't need any specific permission to be set in a field. Okay, we can have a small passive system even on the roof of our house because we don't need any permission. Conversely, when we want to transmit something, we have a lot of limits on the power that we can transmit, the frequency, and so on. So For passive radars, also for the academia, it's much easier to have such system working for experimental and research purposes. So let me show you some example. One of the first that has been implemented is the silent sentry, implemented by Lockheed Martin. And this is a picture actually taken from some document, some Lockheed Martin document, and you see that the silent sentry used the FM broadcast. As I told you, the FM is one of the most common sources of opportunity used for the passive radars. And you see, as usual, the direct signal, the same things that we have seen in the general picture of the passive radars. And you see also here that there are multiples FM broadcast base station. It means that this silent sentry is able to use multiple transmitter and a single receiver. So it can work in a bistatic configuration, but it can work also in a multi-static configuration and is able to detect and to track the targets. Now let's go to see a little bit more. So you see that it uses FM radio station. You see the antenna here in the plot. It is a circular one. As you can see, there are dipoles. The typical configuration has 8 dipoles and a coverage of 200 kilometers. And you see here a plot with, a PPI, so the radar screen where you see the multiple targets that are detected and tracked by the radar. Now, let's see. This is, as I told you, it is possible also to have this kind of system at the university. So this one of the systems that has been implemented at the University of Cape Town, UCT, in cooperation also with the UCL in London. And you see here that you have the receiver, the transmitter, the receiver is on the roof for one of the departments of the University of Cape Town. And nearby there is an airport. So you see that there are all the aircrafts moving here and there, and then they can be seen by the passive radar. Here I have a video that I hope can be seen. So the radar is a small Cessna, and on the left-hand side, you see over time what the passive radar is able to see, and on the right-hand side, you see the output of the CFAR, the CIA CFAR. So you see the detection, and then see that here we lose the target, and then we see it again. So see again, okay, the target that appears and disappeared again. For some time, the target is not seen, and then it is seen again. So this is an experiment that has been carried out by the UCT University. Okay, so this is what you can see with a passive radar, and you can easily recognize that on the left-hand side, There is a lot of clutter, there is a lot of noise and component that must be canceled. And then here you see that after the CA, CFAR, or any kind of CFAR detector applied on the range velocity map, that then really we can see the targets moving at different frequencies and in different positions. Let's go ahead with other systems. This one is the Homeland Alert HA100 that's been developed by Thales and Onera, France. The first version dates back 2005, and it uses 8 vertical dipoles again with FM radio station. The coverage is about 100 kilometers. So again, here there are signal processing algorithm applied for rejecting the DPI, to create the ambiguity function and then to detect the targets. Okay. So let's go ahead. As you can see, this kind of antennas on mast are relatively small, so they can be placed everywhere, and they can be moved easily from one place to the other place. Here we have also the Airbus space and defense system. This is a multi-channel passive radar. As you can see, there are antennas of different kind, and this is able to use FM, DAB, and DVB-T signals. So the usual FM, that are the digital radio and the digital TV. Can be used also for detecting low-flying object, like the UAV with small radar cross-section. And it has a bistatic coverage of 200 kilometers. But again, this can be also used in a network, generally with 2 devices, different detection, different position locations, in order to improve the angular resolution, but also in general the accuracy of the estimation of the target. ALIM is an iron passive radar with a coverage of 250, 300 kilometers, again used for detecting low-flying targets. It's quite strange because it has these parabolic antennas, and in all the other passive systems we don't use the parabolic antennas, but more dipoles to have some kind of beamforming and beam steering. Then here we have the Cora, that is a system that has been designed by Fraunhofer in Germany. And also this system is able to use more than one signal opportunity. In this specific case, it exploits the digital radio, so the DAB, and also the DVB-T. So you can clearly see that there are 2 series of antennas on this mast. The mast can be elongated, so it can reach, it can be much higher, that you can see here in this picture. The upper part of the mast is equipped with 16 vertically polarized antennas, dipoles, for the DVB-T. And the bottom part of the is equipped with the spare dipoles elements for the DAP. So you see here that we have two series of antennas. Then we have this Twinvis produced by Ensolt. Again, you see here that there are the usual 8 dipoles, but the system can be also multi-channel. So it can use the FM signals and also the DAB and the DVB-T networks. They claim to have 360 azimuth coverage and that they can do also 3D tracking. Now let's look at the AULOS, is the system produced by Selex in Italy. And again, there are it is based on the uniform circular array. Also also this one and this one all are circular arrays for the reason that we have mentioned yesterday, because in this way the beam has almost the same shape in all the azimuth direction. That is not possible for the uniform linear array, the ULA. And this system is able to use the FM and the DVB-T, and the system is quite standard because it is able, through the antennas, the uniform circular array, to perform some digital beamforming. And then there are the classical blocks with the DPI cancellation, the generation of the range Doppler map, so the ambiguity function, and the cipher detection before the tracking function. Then we have the system that is produced in Poland, the PET, and this system is able to use the FM and also the DVB-T, but also the GSM. So this is one of the few commercial system or commercial/military system that use the GSM signal. This is very specific, it's a bit different than the usual ones. It is called the Silentium Defense Maverick. It is produced in Australia. And it is part of the Oculus Observatory in South Australia, and actually it uses the satellite-based transmissions. So it is a bit different because it wants to detect the low Earth orbit object, but using the satellite transmission. So passive radars, as you can see, can be used depending on the dimension of the system, depending on the scenario, depending on the available area that we have to set the antennas. Can be used with multiple signals, can be used for multiple missions. Of course, here there are many antennas, but in Australia, particularly in the center of the Australia, the free land is very large. Then there are sites where it is possible to put a large number of antennas. It's not always possible in all the other countries. And then here we can have this, in Australia, they have this big system. So this is just a short list of the available passive radars. But if you're curious, you can just look at Google and search for other systems in different countries. At the end of this lecture, I listed some of the references. If some of you is curious to learn more details on the history of the passive radars and on the details of the passive radars, the highlighted in blue is this book, Signal Processing Passive by Static Radar, because I took some of the figures in this lecture, particularly at the beginning of the lecture with all the geometry from this book. So this person to reference it. And then there are also multiple articles, chapters of other books, even a tutorial with where I use some of the figures in these references for this lecture. So if you are curious, you can look and have more information. Now that we have finished the lecture on the passive radars, then we can move to another topic that is quite important, and it is on the MIMO radar. So let's start with the introduction to MIMO radar system. And in particularly the differences with the phased array radar. Maybe you are familiar with them much more than with the MIMO radar system. So the main difference between the phased array radar and the MIMO radar is that the phased array transmit one single waveform. So each antenna transmit the same waveform, and on receive or on transmit or on both, we can perform beamforming and beam scanning, changing the phases with which we receive and transmit the signals, but the signal is the same. And for implementing phased array, we can perform analog beamforming, we can perform partial digital beamforming or fully digital beamforming. In general, for MIMO radar, we talk about fully digital beamforming with active arrays. Active arrays means that each element of the array has its own receiver and transmitter, so and waveform generator. So it is able, each element is able to transmit its own waveform to be switched on or switched off, or depending on the beam pattern that we want to realize, or the characteristic of the scenario that we are analyzing. And anyway, also as the phased array MIMO radar, you will see that on receive are also able to create multiple beams, and then they can also be used in multifunction radars. But the main difference between the phased array and the MIMO radar is that the phased array transmit a single signal. MIMO radar are able to transmit multiple signals. And these multiple signals generally are orthogonal each other, but it's also possible to introduce some correlation among the waveforms that are transmitted in order to create on transmit the beam pattern that we want. We will see that if we transmit orthogonal waveforms, the beam pattern on transmit is completely flat. So we cannot have on transmit any gain in focusing the beam along one specific direction. But anyway, we will see all these details in the next slides. There are two basic regimes of operation for the MIMO radar. One is where the antennas are broadly spaced. So broad space means that they are far away with respect to the wavelength of the radar and to the distance to the targets. Okay, this means that they are broadly spaced. In some cases, in some books or articles, they are also defined, called statistical MIMO radar, or more generally, MIMO with widely separated antennas. We will say only a few things about this MIMO with widely separated antennas. We will focus much more on the other regime that is much more common. In this second regime, all the elements, transmit array elements, but also the receive array elements are closely spaced. So the target is in the far field with respect to both arrays. And these systems are sometimes referred to as coherent MIMO radar, but the most common denomination is collocated MIMO. In this case, the target scattering is the same for each antenna pairs, so there is only some difference in the delay. So summarizing, the main difference with the phased array is that MIMO radar are able to transmit multiple waveforms, not only one single waveform like in the phased array. There are two different kinds of MIMO radar. One is the MIMO with widely separated antennas, so each element of the antenna on receive and on transmit are far apart. And the second kind of system are the MIMO, where the receive and transmit array elements are close. It is possible that we use the same elements for transmitting and receiving, but they can be also different elements, but still closely spaced. And these systems are called generally co-located MIMO. And this is the kind of MIMO on which we will focus this lecture today. Okay, because these are the most common. What are the advantages of having the MIMO? Well, we will see later on that one of the main characteristics of the co-located MIMO radar is the virtual array. And we will define what the virtual array is and how we build this virtual array. But this virtual array provides us with a high number of degrees of freedom. And then using all this degree of freedom, we can have better angular resolution. We can localize and detect higher number of targets, of course, compared to the phased array. Then we can also work on the side lobes on the virtual array. And what we do digital beamforming at the we could do digital beamforming both on transmit and on receive. Generally, we do it on receive. And then this system, since on transmit, if all the waveforms are orthogonal, don't focus the beam in a specific direction, so they spread. Is there any problem? Okay. So they spread the energy along all the angular direction, then they have a low probability of being detected. So in some cases, they can be considered as a LPI systems. What are the cons, so the downsides of the MIMO radars? The implementation is much more complicated than in the phased array. And for the same reason that I told you that if we transmit orthogonal waveforms, we cannot focus a beam on transmit. Then we have some gain loss because the transmission is omnidirectional. So this is not a problem when the radar is working in search mode, because it is true that we don't have focus on a specific direction, but we can stay on the target for longer time. So we have a large time on target. This could be a problem in tracking mode, of course, because we want to track the target. So generally we have an estimate of the position, and then we would like to focus the power, transmit power along some direction where the targets are in order to increase and to optimize the signal to noise ratio, okay? But actually, this problem can be solved also in a collocated MIMO radar if we introduce some correlation between the different waveforms that are transmitted, and then we can design our beam pattern also on transmit with single or multiple beams. Now, what are the waveforms that are transmitted by the MIMO radar? Now, the desired waveform properties are small side lobes. So we would like to have a high peak in the autocorrelation function, but small side lobes. We aim to have almost orthogonal waveforms, so cross correlation with a very low peak. We would have also Doppler tolerance for signal of interest. I think that you know what Doppler tolerance means. It means that if we our Doppler filter is not exactly centered on the Doppler of the target, we still can see the target. And the chirp is a typical Doppler tolerant waveform with its pros and cons, but we would like to have so waveform with some Doppler tolerance. And also we would like to have some flexibility in choosing an arbitrary number of waveforms and pulse width. So we would like to have some degrees of freedom in the number of waveforms that we want to transmit, and also the shape of the waveforms. And all these waveforms should be easy to implement and also not too costly. So in order to have cheap radar hardware. So maybe too many assumptions or too many requirements. So we will see how we can meet some of these requirements. Now, since we want to have waveforms with this low peak cross correlation response ratio, so we want to have waveforms that are orthogonal or almost orthogonal, then we have three possible approaches to consider. The first one is to have orthogonality in time, so time domain waveform diversity. The second approach is to have orthogonality in frequency, so frequency domain waveform diversity. And the third one is the orthogonality in chord, so chord domain waveform diversity. Now let's see the pros and cons of all the three approaches. The time domain, so the TDMA, is quite easy. And it means that each array element or each subarray emits a signal in a specific time window, and then the other practically in sequence. So suppose that you have a ULA, so a uniform linear array, then the first element transmits a signal in the first time interval, the second element in the second time interval, the third and the third, and so on. So these waveforms share the same frequency band. They share the same hardware, of course, but they are orthogonal in time because they are transmitted sequentially in different times. And in many cases, if we work with this approach, time domain waveform design, then we can use the traditional linearly frequency modulated waveform, so the chirps. So each element of the array can transmit the same chirp in cycle, okay, so one after the other. This, as you can understand, is a very simple approach because we already have this architecture for the phased array. So we don't have to invent or to build anything different. The problem is that since you want to use all the waveforms in order to improve the performance, your pulse repetition frequency actually is reduced by the factor of the number of different pulses that you transmit. So suppose that you have 10 elements of the antenna and each element transmits sequentially one chip. It means that the pulse repetition frequency at the end is the pulse repetition frequency of each element divided by 10. So the pulse repetition frequency actually is reduced by 10. So the number of elements of the antenna of the subarrays that you are using. So the main con, the main pro, let me see, the main upside of this system, or this approach, is that it's easy. You can use the usual waveforms that we know very well, and then we can use the existing hardware. The main downside is the impact on the pulse repetition frequency, with all the problems that we have, because you know that the pulse repetition frequency is strictly related to the ambiguity in range and ambiguity in frequency of a system. So we cannot choose the pulse repetition frequency that we want because this has an impact on the performance of the system. So depending on the scenario, depending on the kind of target that we want to detect, the maximum range of the target that we want to detect, the maximum Doppler of the target that we want to detect, we need to choose the pulse repetition frequency. So we are not completely free in that. We have some constraint. This is an example. You see that in this case, we have only 2 antennas. So in blue, the transmission of the first antenna, in red, the transmission of the second antenna. And you see that each block is first chirp, second chirp, first chirp, second chirp, and so on. Okay, so this is the way sequentially we can transmit the waveforms in a MIMO system. Now let's see the second approach is the frequency domain waveform design. It means that practically each element of the array transmits on a different carrier frequency, and this carrier frequency must be separated enough in frequency in order to avoid the mutual interference. This can be done, for instance, for OFDM. So we can transmit multiple waveforms on different carrier frequency. Again, there is some pro and there is some con in this. The pro is that we can again use partially the architecture and the hardware that we already have. But of course, the instantaneous bandwidth of the system can be very broad, and it means that we need very high speed samplers, so AD converters. It means that this increases the size of the system, the weight, the power requirements, and of course, also the cost of the system. So even though each, for instance, LFM waveform occupy the same bandwidth, but if you choose the carrier frequency, and these carrier frequency are separated enough not to overlap, then when you even when you down convert after down conversion, then you will have a large a broad bandwidth, much broader than the bandwidth of the single LFM. And then you need a very high quality sampler with very fast in order to sample correctly the signal. So this is the main problem. Now, third approach is the co-domain waveform design. It means that the different waveforms that are transmitted by the different antennas occupy the same time, so they are transmitted at the same time in the same frequency bandwidth, but they are made orthogonal thanks to the codes. So they use in a very efficient way the spectrum, of course. So we don't need to increase or decrease the pulse repetition frequency. Then they can be transmitted at the same time, so can be the usual waveforms, but they need this code. And the problem is that it is not easy to implement or to achieve truly orthogonal code waveforms with a finite length of pulses, and it is not possible to create an infinite number of orthogonal code. It means that if you want to have orthogonal or almost orthogonal codes, then we are limited in the number of codes that a waveform that we can transmit. So the main upside of this approach is that we can transmit at the same time and using the same frequency. So we have efficient use of the spectrum, but it's difficult to get through the codes orthogonality with finding the length of the code itself for a large number of codes, so for a large number of waveforms. Now, there are hardware constraints also in implementing the MIMO system due to the fact that we want to transmit multiple waveforms. You can understand that it is much easier if there is only one waveform and each element of the antenna transmit the same waveform, and the only thing that the antenna performs, the system perform, is the phase shifting, either analog or digital. In the MIMO system, you have to generate multiple waveforms, so of course the hardware is much more complex. And so each element has to have its own waveform generator, and then its own independent power amplifier. So for each element of the antenna, we are forced to have a waveform generator and a power amplifier. In hardware, it means also that it is difficult to control the mutual coupling between the different elements of the array. Why? Because if you transmit the same waveform on multiple antennas, the phase differences between each element of the antenna is the same over the time along the transmission, okay, because the waveform is the same. And then we can control in some way the mutual coupling, or what the usual metric that they use for measuring the coupling, that is the voltage standing wave ratio. So we can keep constant this voltage standing wave ratio in the phased array. And then we can, in this way, we can limit the mutual coupling. In the MIMO system, each antenna transmits its own waveform. So the relative phase, instantaneous relative phase, changes with time. So it is not the same during the entire transmission. And then we could have, in some time instant, large reflected signals. It means that if this power is reflected inside the system, this can damage the hardware. So we have these power constraints in the MIMO system. This is also the reason why many MIMO systems nowadays are systems with low power on transmit. So for instance, the vehicular radars, the automotive radars, many of them are MIMO system. And this is because actually the power that is transmitted is not particularly high. So now let's see here in this cartoon the difference between the MIMO systems and the phased array. So on the left-hand side, we see a standard phased array radar. And you see the transmit phased array and the receive phased array. On transmit, you have each element of the antenna that can weight in a different way the same waveforms. So the waveform, the transmitted waveform is ST over time. And in each antenna can multiply the same waveform by a weight. And we use this weight practically to design and to optimize the beam pattern. Then we can focus the beam, the main beam, along a specific direction. We can reduce the side lobes and so on. This is what we do with the phased array. Now, on receive, each element of the phased array receive the same waveform, so ST, and times a coefficient. And this coefficient depends on the targets. So depends on the radar cross-section of each target, it depends on the distance of the targets, and so on, okay? Then in the phased array, as you know, we have again the steering vector, the temporal steering vector, so we can also focus the receive phased array. Here, the two phased array are, plotted, separated, but actually transmit and receive phased array can be the same. But we are not forced to use the same elements of the antenna on transmit and on receive. And the weights on transmit can be different from the weights on receive. Of course, this is possible when we do digital beamforming. And on phased array, the beamforming can be partially analog, digital, partially digital, mixed analog or digital, or fully digital. Now let's go to the MIMO system. The MIMO system, you see that on transmit, we have an array, and theoretically, we each antenna transmit a different waveform. So suppose that we have M sub T transmit antennas, elements, and then we can have a maximum of MT waveforms that are transmitted, okay? All at the same time. And then these waveforms hit the targets, and then the targets backscatters some part of the energy back to the receive array, MIMO receiver array. And the main difference is that actually the signal backscattered from the targets is a combination, okay, of all the waveforms that have been transmitted. And then in the MIMO receiver array after the array, there is for each element of the antenna, you will see there is a bank of meshed filters. Each filter is matched on each of the waveform that has been transmitted. So we gain a lot of degrees of freedom, because we have the degrees of freedom due to the element of the antenna, but also due to the waveform, the different waveforms that are transmitted by the different element of the antenna, of the array. Now, again, here in the figure, we have separated MIMO transmit array and MIMO receive array, but they can be the same array. But again, they can be collocated, but we could use different elements on transmit and on receive, okay? So, but again, the main difference that you should notice here is that since in the phased array we transmit a single waveform, what the receive phased array get is a single waveform delayed by due to the distance of the target and multiplied by some coefficient beta that is due to the radar cross section of the targets, the distance, and so on. Of course, if the targets are moving, we have also the Doppler shift. In MIMO systems, what the receive gets is a combination of the waveform that has been transmitted by the MIMO transmitter array. It is not a single signal. And then the signal processing in the receive is much more complex than in the phased array. In the phased array, practically we have a single meshed filter on the single waveform. In the MIMO receiver array, we have a bank for each element of the antenna. We have a bank on meshed filter, each one on each waveform that has been transmitted. So let's summarize a little bit of the what we have said so far before taking a short break. So suppose that the radar system, the MIMO, has a number of M collocated antennas on transmit, and suppose that it has N collocated antennas on receive. Again, these antennas can be on the same can be the same, so some of the elements of the antenna can be receiving and transmitting, or they can be different, but anyway, they are collocated. Each element of the array are assumed to be close to each other in a space. So, as I said, possibly the same array on receive and on transmit. So they see the targets at the same directions and from the same angle, okay? Then the M transmitting antenna can transmit one different signal for each antenna. So we have a maximum of capital M waveforms, each waveform transmitted by a single antenna. So now at each time instant t, we can build a vector of waveforms appending the sample of each waveform. So S1, S2, Sm. This is for each time instant. Now, the MIMO, original MIMO system, as I said, transmits orthogonal waveforms. What does it mean? It means that the scalar product, so the integral over t sub 0, t sub 0 is the length of the time duration of each pulse, each transmitted pulse. So the integral of t sub 0 of this vector, okay, for each time instant, st times s Hermitian t over t is equal to Im. So it means that this integral is equal to 1 when we have a product of the same waveform. So S1 times S1 conjugate, okay? Then the product is 1. So the waveform is has a unit energy, and so it's normal. But when we make the integral of the product or two different waveforms, say S1, S2, or S1, SM, or whatever, S2, SM, then the product is equal to 0. So the results of this integral is equal to 1 only when the index of the waveform is the same. S1, S1, S2, S2, S3, S3, and so on, is equal to 0 when we do the product and the integral of this product on two different waveforms. This means orthogonality in our mathematical concept. So I think that we are at the top of the hour, and then we can make a short break.
Yes, ma'am.
Okay, 15 minutes break, and we will be back in 15 minutes.
Ma'am, shall we start now?
Yes, I'm sharing the screen.
Okay, ma'am.
Here it is. Okay, so let's continue with our MIMO radar. Then we have defined also mathematically the orthogonality principle. So let's see how it works. So each antenna transmits a different waveform. We call this waveform SM, where M is the index of the transmit antenna. At the point target, okay, so in the plot here, one of these point target, we consider only one target. There is the linear combination, the signal received at the point target is a combination of the transmitted waveform. So see the sum over all the waveforms. And of course, each waveform is weighted with this exponential term that depends on the carrier frequency and depends on the delay. So the time for the signal, this transmitted signal to reach the target. Of course, this tau sub m depends on the position of the antenna element with respect to the target. So each element has a different, since each element transmits a different waveform, each signal has a different delay. And then we can rewrite this sum in this way, defining a new vector that actually is the transmit array steering vector, that is this A. And you see that for each element, so for each signal, we have one different exponential. So we can rewrite this signal received by the point target as the product between these two vectors. One is ST that contains all the transmitted signals, and the other one is the steering transmit array steering vector. So you see each component A1 theta, AM theta. It depends on the carrier frequency, F sub 0. It depends on each delay. And of course, the delays depends on the position of the antenna element with respect to the target at hand, the target that we are considering. Okay, so the signal can be written in a closed form, in a vector form, as the product between these two vectors, the transmit steering vector and the vector of all the signal transmitted by the array. Now, let's go to the receiving array. At the receiving array, we have, of course, the sum of the signal, the received signal, and the noise, okay? The noise, now let's consider as a noise the thermal noise. So with a flat spectrum, but actually this can be clutter, that can be correlated, spatial correlated, and so on. So, but for easy, then let's consider it as a white noise. Now let's look at the X sub S, so the signal that is received by the array. Now, the backscattered signal by the target, by each target, is beta, okay, times the signal received by the target itself. So going back to this figure, you see that each target backscatter a combination of the signal that have been transmitted, okay? So this combination is xg of t, and of course is multiplied by beta, that is target coefficient. But this signal is received with a different delay depending on the position of the elements of the receive antenna. So we have something similar here to what we have seen here. Here there was this coefficient, exponential coefficient here, that takes into account the delay between the transmit signal and the target. Here we need to take into account the delay between the signal backscattered by the target and the different elements of the receive array. Of course, again, these delay are different depending on the position of the target, depending on the position of the elements of the antenna. So we again have another steering vector. This is the receive steering vector, and we call it B of theta. So A of theta is the steering vector on transmit, B of theta is the steering vector on receive. The shape actually is similar because they are both exponential shaped. They depend on the carrier frequency of the radar, and they depend on the delay, single delay for each antenna. Now, this vector has a dimension n because we have n, capital N, receiving antennas, and this vector has a dimension m, capital M, because we have capital M transmitted antennas and transmitted signals. As I already said, tau tilde of n is the time needed by the signal deflected by the target that is located at theta to reach the nth receive antenna. Okay, so this is the model for the received signal xs of t of the target, okay, on each element of the antenna. Now we can rewrite simply reshaping the vectors. We can rewrite the received signal at the antenna, at the receive array, as beta times b conjugate of theta, a Hermitian of theta times st. St is the vector of the signal plus the noise. And then we can define h of theta, this product b conjugate theta, a Hermitian of theta. This is a matrix, okay? And we call it h of theta, st. Then h theta is also called the MIMO channel matrix. So in some way, for each signal, this h is a weight, so it's a coefficient that define the round trip of the signal from the array to the target to the receiving array. Now, of course, each element of h takes into account the delay between the transmitted signal, the target, and receive the signal. Now, from the radar point of view, this notation is not that common, okay? Generally, we use this previous notation that we have written here, but I mean, it is just changed a bit, but the concept is the same, so the elements are the same. This notation with the matrix H, the MIMO channel matrix, is quite common in communication. So this is notation that is used in MIMO communication when H is the channel that generally is estimated, and is estimated to use some pilots, probe signals, and so on, okay? Before we can make any kind of demodulation, we need to estimate the channel matrix. This is done commonly in communication, and that's why they use this notation. In a radar, this notation is not that common, but sometimes in some article or in some book, you can find it also for radar application. That's why I summarize it now, so you are not surprised if you see it in some book. Now, what happens at the receiver? At receiver, each element of the array, as already said, is followed by a bank of filters, matched filter. There are m filters for each element of the array, and each filter is matched on one of the waveform that has been transmitted, so SMT. Okay, so now you have to understand that this system, this is the reason why this system is much more complex than the standard phased array. You have a bank of filters, m filters for each element of the antenna. So if you have n elements of the receiving antenna, you have n times m filters overall, meshed filters, okay? So let's understand how it works, and for the moment, let's ignore the noise, okay? And let's consider the output of the generic meshed filter in the receive array, only concerning the signal, the useful signal. Then let's see the operation that is performed by each filter. So each filter is meshed on one single waveform. So the filter does the correlation between the received signal and each of the waveform. So let's see the output of the M meshed filter at the nth element of the array. So if we go back, this is the model of the signal that we have, the received signal. So you see that is beta. Beta depends on the element of the receive antenna. Beta is the amplitude. So we do beta, amplitude of the target. This is the meshed filter operation, integral over t sub 0, the duration of the pulse. This is the combination of transmitted signals that is backscattered by the targets. So you see the product, A conjugate of theta sub k, say S sub k times t, okay? And then here we have the coefficient that is related to the delay between the target and the nth element of the receiver antenna, okay? Then we do the product between this combination of signal times the matched filter. So this is the impulse response of the M matched filter that is matched of the M transmitted signal. Now we have to remind that that there is the orthogonal property. So it means that when we do the integral, anyway, we can put this beta conjugate n of theta outside the integral because the integral is over t and this beta does not depend on t. Okay, so we can put it outside. Then we are left with the integrals of the sum times Sm. Now we know that actually we can invert the order of the sum and the integral because they are linear operators. Then we are left with the sum over k of ak conjugate of theta, integral over t sub 0 of s cap skt times sm conjugate t. Okay, but we know that from the orthogonal property, if we do the integral of the same signal, we get 1. If you do the integral of two different signals, we get 0. Then, when we do these integrals, we are left with only one term that is different from 0. And this term is the M term, and it is equal to 1. All the others are equal to 0. So the M output at the end of M matched filter is beta times B at conjugate of theta times AM conjugate theta. Okay, so this is the output of the M filter at the M element of the array. Then at this point, we can consider all the output of the M meshed filter on all the elements of the array. So since all elements of the array have the same bank of meshed filters, it means that there will be for each element of the array a matched filter that is matched on the M transmitted signal. So if we put together the output of this matched filter, all matched on the M transmitted waveform, on each element of the antenna, we have a kind of snapshot. But this snapshot is the output of the M matched filter. So we have beta, then we have B, because B, as you can see, depends on the element of the antenna. So we have B1, B2, or B0, B2, B3, B capital N minus 1, okay? We have N, a vector, n-dimensional vector here. And then we have the same coefficient, because this coefficient depends only on the transmitted waveform. So it is the coefficient of the delay on the transmit waveform, okay? So this snapshot relates only to the M meshed filter. It means that for each meshed filter, we have a snapshot. So we have a snapshot for the first meshed filter, the second up to capital M meshed filter. If we put together all the outputs of this meshed filter, append the vector of the first meshed filter, the second meshed filter up to the last one, then we have a vector that is beta, A conjugate theta. This one is the Kronecker product okay, this is the symbol of the Kronecker product, times B conjugate of theta. So if we add to this also the vector of the disturbance at the output of all the meshed filters, then the final vector, that is n times m dimensional, so m waveform that are being transmitted, m elements on the transmit array, n elements on the receiver array. Then we have z equal to beta times a conjugate of theta, Kronecker product, b conjugate of theta plus the disturbance at the output meshed filter. Okay. Now, in short notation, we can call this new vector a conjugate theta, Kronecker product, b conjugate theta as v of theta. And this v of theta is the virtual steering vector. So in a phased array, we write beta times p plus d, and p depends on theta, and it is this steering vector, is a spatial steering vector that is due to the all the antennas that we have. Here we have a steering, and these are in the array, if we have in the phase array, if we have n elements of the antenna and one single signal, of course, the dimension of the steering vector is n. We have n antennas on receive and we have m waveforms. So we have a dimension of the steering vector that is n times m. So it's much, much longer than in the phased array, okay? And we call it virtual steering vector. Why virtual steering vector? Because actually, we on receive, we don't have an array with n times m elements. We have only n elements, okay? On receive, we have this longer steering vector because we have the bank of meshed filters. So because we have transmitted m waveforms. So the large degree of freedom that we have is due to the fact that instead of transmitting one single waveform, we have transmitted m orthogonal waveforms. But since this is not a true steering vector, so we don't have n m elements on the receive and the physical position of the elements, that's why it is called virtual steering vector. So we create it virtually thanks to the bank of meshed filter that we have after each element of the receive array. Okay, so this is quite important because the virtual steering vector is one of the core elements of the MIMO collocated system. Now, if the waveforms that are transmitted are not orthogonal, then the MIMO steering vector can be written in this way. On the side of the receiver, that where we have B, nothing will change. So we have B conjugate theta. On the side of the transmitter, this steering vector is not anymore simply A conjugate of theta, but it multiplies by RS, and RS is the covariance matrix of the signals. So if the transmitted signals are not orthogonal, we need to take into account also this covariance matrix. when the signals are orthogonal, this covariance matrix is the identity matrix. That's why it disappears in the steering vector. So if we have I here, I is the neutral element of the matrix product. So E transpose times A conjugate is equal to A conjugate, okay? And then the steering vector is A conjugate of theta, Kronecker product, B conjugate theta, okay? Now, what happens to D? D is the vector of the samples at the output of the meshed filter. And at the input of the meshed filters, we have the noise W. Now, as I told you, W, that is here, can be white noise or can be correlated noise, for instance, clutter. But take into account that we have also the meshed filter, and then the covariance matrix of the disturbance D takes into account the covariance matrix of the noise at the input, so the noise W, so it is RW. But since this noise passes through the meshed filter, then we need to take into account also the correlation between this meshed filter. Which is the correlation between the meshed filters? The correlation between the meshed filters is the same as the correlation between the transmitted signals, since these meshed filters are meshed on the signals. So if the filters are orthogonal, if the signals are orthogonal, this part of the covariance matrix is equal, so RS transpose is equal to the identity matrix, okay? So we have, if the waveforms are orthogonal, the covariance matrix of disturbance is the identity matrix, Kronecker product, the covariance matrix of the disturbance at the input. So if the waveforms are orthogonal and the noise at the input is white, the covariance matrix at the output of the Doppler filters, so the bank of Doppler the meshed frequency, meshed filters, is the covariance matrix is equal to I, because I Kronecker product I is again n times nm times nm, so nm dimensional identity matrix. Okay, so summarizing, this is the virtual steering vector, that is the Kronecker product between the steering vector on receive, on transmit, or A, and the steering vector on receive, B, and it is called V. What happens to the disturbance D? If the signals are all orthogonal, the covariance matrix is I, Kronecker product, or the covariance matrix of the noise at the input of the meshed filter. If the input of the meshed filter was a white noise, the noise at the output, D, is again a white noise. If there is some correlation among the waveforms that are transmitted, then the steering vector is given by the covariance matrix of the signals times A, the steering vector on transmit, and then Kronecker product with the steering vector on receive. I hope this is clear, because this is one of the main point of the MIMO system. Now, let's consider the specific case in which both transmit and receive arrays are uniformly linear arrays. As you've seen so far in the definition of A and B, that are the steering vectors, we have not done any hypothesis on the shape of the antenna. We simply put here the delays, okay? Tau tilde sub 1, tau tilde sub n, and we have done the same here, all the tau n of theta. So we have not specified any shape of the antennas. We have just indicated tau. So this equation here with the virtual steering vector is valid whatever the shape of the array. But now let's simplify things and let's go to the ULA, so the uniformly linear array. In this case, we have seen that actually that in a uniformly linear array, the distance between two different elements is just dt on transmit and dr on receive. And dt and dr can be the same, can be different. It means that the difference in the delay on the different elements of the antenna is related to the distance between the elements of the antenna and also to the theta, sin theta, the angle in view of the target. So it relates to the position of the angle, the direction of arrival of the target, as you can see here. Okay, and it is the same also for the receive antenna. We are supposing that both systems are collocated. It means that they see the target from the same angle, theta, okay? And then here we have that the distance is the delay, the differences in the delay are related to dr and sin theta, okay? And you see here that after each element of the antenna, there is a meshed filter bank. So n waveforms, there is a filter bank of m meshed filters, as we have already seen in the previous slides. So in this case, we can write in a easy way the steering vector on transmit and on receive as a function of the distance between the elements, dt, and as a function of the direction of arrival of the target, that is theta. You see that this vector is m-dimensional, and this vector is n-dimensional. D sub t and d sub r, as already said, are the inter-element spacing. So the space between one element and the other element in the transmitter and in the receiver respectively. They can be the same, they can be different. Now, let's look at the shape of the virtual steering vector. The virtual steering vector is the Kronecker product between the steering vector on transmit and the steering vector on receive. So if you look at the shape, in this case, of the virtual array, then you see here that when we are on the M meshed filter and N elements of the antenna, then we see that the elements of the steering vector of the virtual array steering vector has this shape. So you see the same wavelengths and so on, but you see m d sub t sin theta plus n dr sin theta. So the position, the exponential of the virtual steering vector depends on the distance dt on transmit and dr, the position of the meshed filter, the position of the element on receive, and the angle, the looking angle or direction of arrival of the target. So practically, it means that if you look at this coefficient here, the virtual steering vector can be built convolving, so make a convolution between the location, so the position of the real transmitter and elements of the antenna, and the receiver location. Now, this could seem a little bit strange. So at this point, we could wondering, what is she saying? So what is the meaning of that? Now let's go ahead with an example, and maybe it will be clear after this example. So let's consider a monostatic configuration that is quite usual. It means that the transmit array is the same as the receive array, okay? And then suppose that we have we use all the elements for both transmitting and receiving. So it means that we have m waveforms, but m is equal to n, the number of receiving elements. And suppose that the elements are separated by d that is equal to half the wavelength. We have seen yesterday, looking at the beamforming for passive radar, that the ideal distance between elements in the phased array is equal to half the wavelength. Of course, as I said yesterday, this is not true only for passive radar, but it is true for every kind of array processing. So every kind of array for active radars, passive radars, for communication systems, and so on. Because with this distance, we exploit all the maximum length of the antenna, and we do not create any grating lobes, so any ambiguity in the beam pattern. So this is the ideal distance between elements. Here, it is the same distance on receive and on transmit, because we are using the same array and we are using all the elements both on transmit and on receive. Okay, now suppose that then n equal to m is equal to 3, and then suppose that we have this position for the elements. We have 1, then we have lambda divided by 2, and then we have another elements, and then lambda divided by 2, and then we have another elements. Now, if we consider that m can have the values in 0, 1, and 2, and also m can have the same position, 0, 1, and 2, and the dt and dr are the same, okay? It means that we can practically, here we have m plus n times lambda divided by 2 sin theta, okay? So let's see the values that m plus n can have. Of course, 0, plus 0 is 0, then 0 plus 1, 0 plus 2. Then we have 1 plus 0, 1 plus 1, 1 plus 2. And then we have 2 plus 0, 2 plus 1, 2 plus 2, okay? Then inside this argument, then we can have the same number multiple times. So, for instance, you can obtain 1 adding 0 plus 1, so m equal to 0 and n equal to 1, but you can have also 1 plus 0, so you have twice, okay, twice the same virtual position in the virtual array, okay? What about, for instance, 4? You can obtain 4 only if m is equal to 2 and n is equal to 2. What about 3? You can obtain 3 if you have m equal to 1, n equal to 2, or n equal to 2 and n equal to 1. So you see that there are multiple choices, multiple combinations. So you can obtain the same virtual position multiple times depending on the value of m and depending on the value of n. This is kind of convolution because practically you have position that is repeated only one and only one, then it is repeated twice and twice, and it is repeated 3 times. So it means that the array aperture is much larger. So the array at the beginning was at a dimension of 3, now it has a dimension of 5. So exactly it is 2 times n minus 1 distinct virtual elements. But some of these elements is repeated multiple times. So this first position repeated only 1, this twice, this 3 times, twice, and this 1. Okay. So we could build a virtual array when all position is repeated just once instead of having this over representation, build in a proper way one of the arrays, the transmit array or the receive array. Instead of using exactly the same array on receive and on transmit, we can use 2 different arrays or the same physical array but the different elements of the antenna. And then we can build a virtual array that is much longer with a minimum number of elements. Now, let's look at practically, this is a cartoon of what we have seen before. So supposing that we have this transmit and receive array. Here there are 8 elements, as you can see. They are all separated by half lambda. And then you want to build your virtual array. So your virtual array is this one. So you make all possible combination of m and n. Mathematically, this is a convolution between these positions and themselves, okay? And then how do you do the convolution? You translate the vector and you do all the products. It means that for this position, you have one single combination. For this position, you have 2 and so on, 3, 4, 5, 6, 7, 8, and so on. If you remember that the convolution between a rectangular signal and itself is a triangle. And you see that the position here are as a rectangular signal, and at the end you get a kind of a triangle where the height of the triangle is the number of times that the same position is repeated in the virtual vector. Okay? Now, can we do better? So in this case, we are using 8 elements on transmit and 8 elements on receive. Can we do better? We want to build an array with the same length, but without repeating the same position multiple times in the virtual array, because they actually don't add information on the signal because they are exactly the same value, okay? So they don't add anything. Now let's try it in this way. Let's take again contiguous virtual array, but in this case, the transmitter and the receiver position are independent. So let's take a first array. Suppose that is the transmit array with 4 elements in the antenna, and each element is separated by lambda divided by 2, okay? And then we have this position. Now, suppose that the receive array, instead of using all the 4 elements, use only the first, use only 2 elements, okay, instead of all the 4. And in this case, the distance between the elements, instead of being lambda divided by 2, is 2 lambda. It is exactly m, the number of transmitted elements, times the distance between the elements of the transmitted array. Okay, so dr is 2 lambda. In this case, we have only 2, and we're supposed to have only 2 elements. Okay, now let's build the virtual array. So the receiving antenna, in this case, the positions on the receiving antenna are 1, then after lambda divided by 2, we don't have any elements. Lambda divided by 2, we don't have again any elements. We don't have here any elements. We have an element here. And the distance between this element and this element is exactly 2 lambda. So lambda divided by 2 plus lambda divided by 2 plus lambda divided by 2 plus lambda divided by 2 is exactly 2 lambda. So m times dt. This array is a sparse array. It is sparse because only few of the positions are occupied, only the first and the last. The 3 positions in between are not occupied by physical elements of the antenna. Now let's look at the virtual array. The virtual array has n times m, 8 elements. Okay, we have 8 elements, and each position is repeated only once. So in this case, we were able to build a virtual array with the maximum possible length, but with the minimum elements of the array, because one of the array is sparse. Now, we can do the same, we can obtain the same virtual array if we use a sparse array on transmit and a full array on receive. So we can interchange, okay? We can exchange the position of the transmit array with those of the receiver array. Nothing will change. We obtain the same virtual array with the same position. Now you should understand that this virtual array is quite important. It's the main elements of the collocated MIMO system, because this virtual array actually determines the behavior of the MIMO system, okay? And it is obtained thanks to the waveforms, the multiple waveforms that are transmitted, okay? So the virtual array is the core element of the MIMO system, and it determines the behavior of the MIMO system. Now let's look at this example. See, we have actually the same EULA, but we have in the red squares are the receive elements of the antenna, and the black circles are the transmit elements. As you can see, the transmit antenna is sparse this time, and the receive antenna is full. This is the virtual array. In the virtual array, we have a full array that is much longer, okay? It is 2 times 8, so 16 elements we have. It is full, and the positions are repeated just once. And this is a ULA, but we could play with the receive elements and the transmit elements also to build, for instance, a rectangular array. So we put the transmit elements on vertical, again the 2 black circles, and then we have a uniformly linear array, horizontal, on receive. Now the virtual array is a rectangular array, as you can see here. Okay, so we can play also with this dimension, going from one to the other, in order to build a longer ULA, or also an array with a different shape. Now, what are the upsides, so the advantages of having this virtual array? So this large number of degree of freedom in a MIMO radar compared to the phased array, for instance. Okay, I'm not going to details everything and how these values have been derived, but it is important to accept that if we have m transmitted waveforms that are orthogonal, and we have n receive antennas, the number of targets, depending on the position of the elements on transmit and on receive, can go from twice practically the sum of m plus n to twice the practically, since it's 2 divided by 3, we can say we can go from the sum, approximately the sum of m plus n, and the product of m and n. This is in the MIMO system. In phase array, we transmit a single waveform. So the number of maximum target that we can detect is practically approximately the number of elements of the antenna minus 1, okay? So you understand that if m is high, is much higher than 1, then the number of targets that can be separated, that can be detected by the MIMO radar compared to phased array is much, much higher. How can we see that? We can see that in the accuracy of the estimation, and we can look at the Kramer-Rao bound for this reason. The solid blue line is the accuracy in the estimation of the direction of arrival of a target in a MIMO radar. And the dotted red line for the phased array. We have n equal to m, 10 antennas. In these cases, we are using a full array on transmit and on receive. And to estimate the DOA, we are using 256 snapshots. So, and you see that for the MIMO, the max is between 5 and 33. For phased array is 6. So you see that actually when we are close, we increase the number of targets. See, the Kramer-Rao bounds increases. It means that the accuracy in the estimation of the DOA decreases, so get worse and worse. In the MIMO radar, we still have the same accuracy, increasing the number of the targets, at least up to 12. Okay, so you see that there is a big difference. And we can see also this when we use n equal to m equal to 5. So, but in this case, we are using on receive a full array and on transmit a sparse array. And in this case, you can see since the on transmit, we have only 5 waveform. Okay, the maximum for the phased array is 3, and you see that after 2, the Kramer-Rao bounds start increasing to infinite for the phased array, but still for the MIMO array, we are up to 12. Okay, and even for 14 and 16, the accuracy is still reasonable. So you see that this is a big advantage of the phased of the MIMO radar compared to the phased array. Okay, now it seems to me that now we have to take a long break, half an hour break, and then we will go back to the lecture.
Yes, ma'am.
See you in half an hour.
Okay, ma'am.
Are you ready to start?
Yes, ma'am.
Okay. So share again the screen. Here it is. Can you see it?
Yes, ma'am.
Okay, perfect. So let's continue. Next our on the MIMO radar, and we have seen the waveforms. So we have seen the output of the signal of the system with the virtual array. We have seen the virtual array shape when we adopt two ULA arrays for on transmit and on receive. So we have seen the sparse array in this analysis of the virtual array elements. And then we have seen also that the larger degrees of freedom of MIMO can allow us to detect and we estimate the position with good accuracy of the larger number of targets that in the best situation is proportional to the product of the m times n instead of the simple number of n, that is the number of transmitting receiving elements in a phased array. Okay, so now let's look at the beam pattern. That is another important quantity that we should look in the phased array and in the MIMO system. Okay, how the beam pattern is defined. The beam pattern is the power of the transmitted signal, so at least the average if the signals are random. So let's write, as we have already done, the combination of the signals that is transmitted is xt, is the sum of all the signal SMT times the, of course, the delay and AM conjugate of theta. So we know that xt, that is also the signal in every point of the space, is the product between the rho A and the vector st. So the beam pattern is the power of xt as a function of theta. So it is the mean square root of xt. Then let's write it as a Hermitian theta st times S Hermitian st Hermitian at. Then since A is deterministic, then the mean value E goes inside. So we have the mean value of st times S Hermitian t times a theta. By definition, the mean value of the vector st times S Hermitian t is the correlation between the signals S that we are transmitting. So from this equation, we can see the impact of the correlation of the signals on the shape of the beam pattern on transmit. Okay, so for analyzing the impact, suppose that the covariance matrix of the signals is autoregressive of order 1 like. So it means that it is characterized only by the 1 lag correlation coefficient. and see, let's see the impact, so the shape of the beam pattern on transmit, changing the values of this one lag correlation coefficient. You should observe that there are two extremes. When the correlation coefficient is equal to 0, it means that the signals are orthogonal. Okay, so we are in the ideal case of the MIMO radar, when all the coefficients, when the one lag correlation coefficient is equal to 0. When the correlation coefficient is equal to 1, that is the other extreme, it means that all the waveforms are fully correlated. It means that actually the MIMO radar is a phased array, because the signal, the phased the array is transmitting the same signal on all the antennas. Okay, so we have two extreme cases. One lag correlation coefficient equal to 0, so the waveforms are orthogonal, and we are in the MIMO case, in the ideal MIMO case. And then correlation coefficient equal to 1, fully correlated waveforms, phased array. So let's look at the beam pattern. This is not in dB scale. This is in linear scale, but you can clearly observe it, the shape. So rho equal to 1, phased array, fully correlated waveforms. And you see that there is a clear main lobe, and there are the side lobes with a kind of sinc squared function. Okay, so you see that this is the typical beam pattern of a phased array. Now let's decrease the value of rho from 1 to 0. So rho equal to 0, okay, means that we are transmitting orthogonal waveforms. And we have the green beam pattern. The green beam pattern is flat. It means that we are not focusing the energy or the power in any direction, but we are transmitting the same way in all directions. Okay, so the beam pattern on transmit of a MIMO radar, where all the waveforms are orthogonal, is flat. There is no any focus, there is no any gain in any direction. And you see that changing the one lag correlation coefficient, then you can change the shape of the beam pattern. Of course, this is a very easy model for the correlation between the waveforms. We could do much better. We could even optimize the correlation matrix in order to design a specific beam pattern. This is just a toy example to show you that going from 1 to 0, we move from the phased array case, where the waveform is the same, to the MIMO case, in which all the waveforms are orthogonal. So in MIMO radar, when the waveforms are orthogonal, the beam pattern is flat. There is no any focus anywhere. Okay, that's why at the beginning I told you that this can be considered a downside, because we don't have any integration gain, integration in terms of angles, or spatial integration. We don't have any gain in that, because we are not focusing in any specific direction. This, of course, is on transmit. We will see that actually we can do a good beam forming on receive. So summarizing what I already said, when rho is equal to 1, the correlation matrix is 1 times 1 transpose, where 1 is a vector of only ones, and then phase array. Rho equal to 0 means that the correlation matrix RS is equal to identity matrix, orthogonal waveforms, and then we have flat, we don't have any main beam. But we could work on the correlation matrix of the signals to optimize the beam pattern. Okay, now we have seen the beam pattern on transmit. Now let's look at the total beam pattern. So at the beam pattern after the meshed filter. Okay, so at the receiver, and we see that actually, we will see that actually we can obtain a beam pattern that mathematically is equivalent to the two-way transmit receive beam pattern of traditional phased array. Okay, so the antenna pattern, antenna beam pattern, we can calculate it in this way. As usual, we have the steering vector v theta, and then we can introduce a filter that weight the steering vector, the virtual steering vector, that is quite similar to the virtual steering vector itself, but in this case theta sub 0 is a specific desired steering azimuth. And then we can calculate the square, and modulus square is a function of theta, and see what happens. So how this B pattern is designed. When we do the modulus, then we can rewrite the virtual steering vector V is a function of theta or as a function of theta sub 0. And then we have the Hermitian times the vector itself. This is the way we calculate the modulo squared. And then remember that the circle with the cross is the Kronecker product. Okay, so we need to work a bit on this Kronecker product. And we use this property that the Hermitian of the Kronecker product between two vectors A and B is equal to the Kronecker product between the Hermitian of each vector, so A Hermitian Kronecker product with B Hermitian. And then we use also this property that A Kronecker B C times C Kronecker D is equal to AC, so A times C, Kronecker B times D. These are properties of the Kronecker product. So let's apply it. Then we rewrite the product, and then we see that since we have in the first term, we have the Hermitian of a Kronecker product, then we will have the Hermitian of A conjugate Kronecker B conjugate. Then we have Hermitian of A conjugate, that becomes A transpose. And then we have Kronecker B conjugate Hermitian, that became B transpose. Then we have A transpose Kronecker A transpose. It means that with the second property, we have A transpose A Hermitian, Kronecker B transpose B Hermitian. Okay, and then in this case, what we have, that we have A transpose theta 0, A. Keep in mind that in this case, we have this A transpose theta times A conjugate, then we have a B transpose B conjugate, and then practically the modulus of this product can be written as the product of the two modulus square. And then we have A Hermitian theta 0 A theta squared, B Hermitian theta 0 B Hermitian. You see that there is a little different notation because the first was A Hermitian and then the conjugate. But actually, if you conjugate every term, nothing will change because at the end, we are making the modulus square. So if you conjugate each term, A transpose become A Hermitian, A conjugate becomes A, B transpose becomes B Hermitian, and B conjugate becomes B. So that's why the second notation that we see in at the end, okay? And that's if you look at this product, then you see that the first part depends only on the A vector, okay? So the steering vector on transmit. The second part depends only on the steering vector on receive. So practically, even though on transmit we don't do any beam forming or beam steering because the beam pattern is flat, at the end, at the receiver, thanks to the virtual array, we get a beam pattern that is the product between the beam pattern that we could obtain with a phased array on transmit with the steering vector A, and the beam pattern that we could obtain on receive with a phased array with a steering vector B. Okay, so the overall beam pattern of a MIMO radar after the matched filters, so after the we using the virtual array, is the product between two beam patterns. The first is what we could obtain with the steering vector in a phased array on transmit, and the other one is the beam pattern on receive of the same phased array. This is not a peculiarity of the MIMO radar. So you see here in this picture, there is a conventional phased array with 8 elements, and the distance between each elements is half wavelength, so the typical distance, and the frequency is 1 gigahertz. So in the plot, you see that in black, you have the beam pattern only on receive. So practically the first part, A Hermitian times A. In the gray solid line, you have the two-way. So since the array is the same, A and B in the phased array are the same. So practically is the square of the beam pattern on transmit. This is the two-way. With the circles, you see the MIMO beam pattern with a virtual array that is given by the Kronecker product between A and B. And you see that actually the MIMO total beam pattern is exactly what we could obtain with a phased array on receive and transmit. So making the same beam pattern on transmit and on receive. The MIMO is the product between the two. Okay, so overall, we obtain on receive a very good beam pattern. So don't be confused by the fact that actually if we transmit orthogonal waveforms, we don't do beamforming on transmit. We do it directly on receive, and we can obtain a good beam pattern depending on the virtual steering vector that we build. So depending on how we use the antenna elements on transmit and on receive, depends on the shape of the antenna, if it is a ULA or if it is a circular uniform array or a rectangular or whatever the shape. Okay, now let's look at another example. In this case, we have the, let me see, the solid line, black, is the beam pattern on receive. Maybe we can start on transmit. So on transmit, this system is in this way. This system has three elements on transmit, and they are spaced by half wavelength. So on transmit, we have a very short array, but with the ideal distance between the elements. So it's half wavelength. On receive, we have 8 elements, so much longer, but this is a sparse array. So the distance is practically 2 lambda, okay? So this is sparse, so does not respect the half wavelength distance. So let's look at the transmit beam pattern. What we could obtain with a phased array ULA with 3 elements separated by half wavelength. And you see that actually, since we have only 3 elements, we have a very large, very broad main beam. Okay, it's the dotted line, black dotted line, very large. So very broad. We don't have a good resolution. Now let's look at the beam pattern on receive with this ULA with 8 elements that are spaced by 2 lambda. Now this is the situation that we have seen yesterday about the sparse arrays. Practically, here we are not expecting the half wavelength spacing, and then we are using a space that is much longer than half wavelength. So we are creating the grating lobes. So look at the solid line that is in black, and you see that there is a very narrow main beam. This is because the length of the antenna is 8 times 2 lambda, so the antenna is long. The problem is that since we are not using half lambda, then we are creating the side lobes. And you see that there is a large peak at 90 degrees, but there are also large lobes at 60 degrees, 120 degrees, 0 degrees, and 180 degrees. So these are all the grating lobes that we don't want. So if we use a phased array with this beam pattern, we get confused. So it's not easy to detect the target because, I mean, other spurious target as well as the clutter can enter the antenna through the side lobes. So we have some ambiguity. But if we do the product between these two beam patterns, this will be the two-way phased array beam pattern. And it is the same as what we obtain with the MIMO radar, with a steering vector whose virtual steering vector is the Kronecker product between the steering vector of three antennas separated by the half wavelength and a steering vector with 8 elements separated by 2 lambda, so a sparse array as we have seen in the previous slides. And you see again the dots, the light dots that represent the MIMO, excuse me, the MIMO beam pattern. You see that in this way, making the product will still have high side lobes corresponding to the grating lobes that we have on receive in the steering vector, because the steering vector on receive is sparse. But anyway, we have a good reduction due to the product, and then we have a very narrow main beam, and then we have some side lobes. So as you can see, we can obtain with a decent number of elements a good beam pattern, considering that the MIMO beam pattern is the product between the beam pattern on receive and the beam pattern on transmit of the corresponding phased array. Okay? Now, let's go ahead and consider the fact that actually we have multiple pulses. So what we have seen here is what we obtain even with this virtual steering vector, is what we obtain with a single pulse. So this is a single pulse, single snapshot. But generally, we don't work with a single pulse. Each radar, and so also the MIMO radar, works with multiple pulses. And if we have multiple pulses, say if we have L pulses, then considering also the temporal changes, then we will have a new steering vector that in this case is a space-time steering vector that we can call Q. And this steering vector is again the Kronecker product between the steering vector, virtual steering vector, spatial steering vector V that we have seen as a combination of the transmit and receive steering vector of the MIMO, and P that depends on the Doppler frequency of the target. Okay, so PFT. In this case, if we consider L pulses, then we have a vector that is N times M times L long. So a very long pulse. Okay, so the dimension of the observed vector in a MIMO radar can be very large. It depends on the number of the transmit waveforms, the number of elements on the antenna or receiver, and it depends on the pulses in the coherent processing time, so L. If we want to estimate, for instance, the disturbance correlation, then we need a huge number of secondary vectors because the dimension, because the secondary vectors, the number of secondary vectors to estimate the covariance matrix of the clutter, of the disturbance, should be at least twice the dimension of the observed vector. If the dimension of the observed vector is n times L times L, you understand that the number of secondary vectors can be huge. Suppose that we have n equal to 8, m equal to 8, and say that even if you consider two pulses, we have 8 times 8 is 64, times 2 is 164, and that 64 times 8 times 8 is 64. Complex, okay? So, well, this is summarize something that we have already said about the fact that there is no focusing, beam focusing on transmit, and then we do it only on receive. But clearly we can stay on the target for a longer time, so we can have a time on target that's much longer on transmit, because the beam pattern illuminate everything around. And we can also change a little bit the beam pattern on transmit if we don't use omnidirectional elements, but we use directional elements. Then in this case, on the transmit beam pattern, we should introduce this new element that is the shape of the beam pattern of each element. Okay, so the expected gain resolution thanks to the long time on target. Long time on target anyway means that we make the detection complex, because we have a large number of samples that we need to integrate. Okay, so one of the these very low, these are flat beam pattern, so the omnidirectional beam pattern comes with another pro, that the same energy, instead of being focused on a specific direction like the phased array does, is spread in a very large field of view. It means that locally the spatial power density is low, and then it is more difficult to detect the presence of the radar. That's why we say that we have a low probability of intercept in a MIMO radar. because I will skip the details because this is quite difficult. But I want just to say that there is also derivation of the MIMO ambiguity function that is much more complex than the ambiguity function of a phased array or ambiguity function of a standard radar. This is due to the fact that actually we have this steering vector that is virtual, so not easy to write it, but it is possible. I mean, here there is a kind of summary of the ambiguity function. Keep in mind that we obtain the ambiguity function as the output of the matched filter, where the filter is matched to the signal that has been transmitted, and the input is a signal that is delayed and shifted in frequency. Here we have the problem that we don't have a single signal. We have multiple signals. And we have a bank of meshed filters. So the radar ambiguity function is practically should take into account the fact that we have not only multiple antennas, but we have a multiple signal transmitted. And then it's much more complex than the ambiguity function of a standard radar. So I will skip it, and I will leave anyway the slides. We'll provide the slides to you. So if you are curious, there is also the reference to the paper where the ambiguity function of a MIMO radar has been presented. But normally while for the phased array or for the radar, standard radar, the ambiguity function is sometimes used for optimizing and designing the waveforms. The ambiguity function of a MIMO radar is rarely used for optimizing the waveforms. Generally, we look at the beam pattern. So we introduce some correlation on the waveforms in order to optimize the beam pattern. So the virtual steering vector beam pattern after the meshed filters. So that's why maybe we can skip it, because in practical situation, we don't look at the MIMO ambiguity function. There is a definition, but it's very complex. Now let's look at one example of use of automotive radar. This is a demo actually, and for autonomous driving vehicle, and you see that there are four radars, four MIMO radars here. There are one in the front, then there are two in the blind angle, and one on the side, okay? This is a 10 millimeter wave automotive radar sensor, the front, rear, left, and right sides, as you can see, okay? So actually there are, I don't think they are four, they are five, because there are one on the front, two on the angle, and then one at the left and the other one at the right. So there are five different sensors. And actually we could put more sensor also on the back, and fuse the data coming from the multiple MIMO radars, and also with cameras that can be put on autonomous vehicle. Anyway, in autonomous vehicle, both cameras and the radars can play fundamental role for both the cruise control and the parking, the obstacle avoidance, and so on. The advantage of radars, as usual, compared to other sensors like the camera, is that radars don't need the light. The camera needs the light, so they don't work well in the dark. And the radars are also all-weather sensors, so they can work whatever we have fog or rain. The camera cannot work in the same situation. So that's why radars are in many cases used in autonomous driving vehicles. In some vehicle, we can use also LiDAR, so a kind of radar, but based on the LiDAR, okay? And here you see some example of the configuration of the antenna in the radar. You see the transmit, where the distance is dt, and or receive, then we have a distance that is 2dr, so the virtual array is with multiple, with 7 pretty practical elements on the distance of dt. And the second configuration as a sparse array on transmit, and another array on receive. And then you see the configuration of the virtual array. So there are multiple ways also of transmitting the pulses. The first one is the time division multiplexing. So first the red curve, then the green element, so first the red, then the green, red, green. So the virtual is red, green, red, green, red, green. And the other one could be the Doppler division multiplexing, DDM, that is similar to the frequency division multiplexing. Okay. Now, in MIMO for automotive radar, we use MIMO systems, but we use also continuous wave radars. So there are two different kind of radars for automotive, and we will see some example when we look at the continuous wave radar. One of the examples that we typically do is the automotive radar. It is good to use the MIMO radar because we can obtain a very high resolution in angle with a limited cost, and this is important for on a cheap systems. Of course, we need to work at high frequencies, or in this case, the antennas are small, okay? And then also we can use multiple radars, as you have seen in this picture, and we can fuse data coming from different radars in order to improve the resolution and the accuracy of the estimation. So in automotive radars, there are again the TDM mode, the DDM mode that is similar to the FDM, but we transmit chips. And then there is also the FDM scheme where the signals are modulated by different carrier frequency. Here in DDM, actually, we use different chips that are transmitted sequentially, okay? Then you see here one, this is a card, a board for an example of TDMA MIMO. This board is produced by Texas Instruments, and I mean, it's quite popular also for research activities on automotive radars, easy and small. And we can see here it's the same scheme in the center in the beige part. There are all the elements of the antenna of the phased array. I mean, not the phased is not a phased array system. It's a MIMO system, but you see that there are multiple antennas, EULA, and these are the position, and there are multiple arrays on receive. You see the B, C, and A, and it is also possible to combine this array on receive in order to create a kind of rectangular array. So we have some resolution not only in azimuth but also in elevation. In elevation, we don't need a large field of view, because actually in elevation the radars are used particularly in automotive application to detect the obstacles, the objects that are on the road, or the obstacles in the very low obstacles in the parking lot or on the roads. Okay, so the elevation is used for this reason. The azimuth, of course, is used for detecting the other cars, for detecting the obstacles, and so on. And you see here that there are full subarrays. For instance, array B, array C, and array A are full subarrays because each element is separated by half lambda, okay? You see 0.5, 0.5, 0.5. But if you look at the other array at the bottom, then each antenna is sparse because it's separated by 2 lambda. Then we can use the array B in conjunction with the bottom array, the array C, and the array A. Then we build different shape of the antennas. And we have also the vertical elements. The vertical EULA is a full array because each element is separated by 0.5, so half the wavelength. So this is one possible configuration in this board. And depending on the application, depending on the scenario, the experiment, then we can combine the output of these antennas in order to design the beam pattern that we want. Now, let's go to the MIMO, the MIMO with separated antennas. In this case, the configuration is completely different because the advantage here is not the virtual array. The advantage here is the spatial diversity. So practically, we look at the same target from different angles. If you go back to the MIMO, this collocated MIMO, when we look at the initial definition of A and B, you see that actually the angle theta is the same. So it means that both on receive and on transmit, all elements are looking at the target from the same angle. Of course, the distance is different, but they are looking at the target at the same angle. It means that the amplitude beta is the same for all the elements of the antenna. As a matter of fact, here, when I write the expression of the signal, the received signal, I say here beta times the virtual array vector, the virtual steering vector V. It means that beta is the same for all the elements on the antenna. So we are looking at the target from the same dimension. It means that if the target, for instance, is moving, is rotating, whatever it's doing, it is possible that in some cases the instantaneous radar cross-section and then the amplitude of the target is small. And we know that the target can scintillate. The only stable radar cross-section that we see is that of a sphere, because whatever the angle of view, the sphere has a constant radar cross-section. So if the sphere rotate, then the amplitude that we see is the same. But if you put a normal target, aircraft, a car, and you let it move or simply rotate, then depending on the angle of view, you see a different surface of the target, and then you see a different amplitude. So the instantaneous radar cross-section can be very different. So it can happen that in some time instant, even though you have so many antennas, you have a very large virtual array, you have a lot of degrees of freedom, you don't see the target because the instantaneous signal to noise ratio is too low. Okay, so this is the problem of all the radars. This is the problem also of the collocated MIMO radar. But this problem is a little bit mitigated. It's mitigated when we look at the target from multiple perspectives, multiple angles. And this is what distributed MIMO radar, so a widely distributed MIMO radar can do, because actually the antennas look at the radar from different angles. So we gain for the angular spread, we gain in a spatial diversity. And this is an advantage, maybe the main one with respect to the collocated MIMO radar. The problem is that the coherent integration, so using multiple antennas on receive and on transmit, using multiple pulses and integrated them coherently, so the output coherently, is possible, or at least is easy to implement when the antennas are collocated. In this case, it is possible to maintain the same reference phase for all the antennas, for all the pulses in the coherent interval. And then we can gain on receive in terms of signal to noise ratio, in terms of resolution and so on, frequency resolution and so on. The problem with the widely distributed MIMO system is that since the antennas are far away, in many cases, it's impossible to maintain the same phase reference. And then the coherent integration is almost impossible. So there are pros and cons. And then the coherent integration on receive is one of the major advantage of the collocated MIMO radar. Here, if we are able to integrate in some way the pulses, then we can exploit the spatial diversity mechanism, okay? So let me conclude actually, and let me say that I mean, what we have seen so far is actually the structure of the MIMO radar, the collocated or widely located. How can we use the MIMO radar for detection or for tracking? In exactly the same way we use the phased array, okay? So once we are here, for instance, in the collocated radar, that we have the observed vector, multiple pulses, and the virtual array, and then we can build our optimum detectors. And then we can apply the Neumann-Pearson criterion. We actually came out with the optimum or suboptimum detectors, depending on the knowledge that we have about the clutter covariance matrix. Keep in mind that now the clutter, if we use this steering vector, space-time steering vector, then we have a correlation of the clutter that should take into account the spatial correlation and the temporal correlation. And we have seen that the dimension of these vectors is quite high. Then if we don't know the covariance matrix of the disturbance and we have to estimate it, we need a large number of secondary vectors. But mainly, at least theoretically, the detectors that we can implement after the bank of meshed filters, and then when we get the long steering vector, the long observation vector, we can apply the same techniques. So we can apply the same optimality criterion than in the regular, the normal phased array or in the radar. So there is no difference in that sense. Of course, it is much more complex to implement it. So that's why in modern literature there are many papers that try to simplify also the detection and the estimation in the direction of arrival estimation in MIMO. In order to reduce in some way the dimensions of the vectors that we need to use. But the basics on MIMO radar are these ones. So once you get to the virtual array, then you have all the elements in your hands to build the detectors. Okay, so this finish a little bit early the lectures on MIMO radar. So we have, instead of 10 minutes, we have 15 minutes to wrap up and for the questions. The wrap up of the MIMO system is short, in the sense that we have seen two different regimes. The widely located MIMO system and the collocated MIMO system. We have seen that for the widely located MIMO system, the main advantage is the spatial diversity, the angular diversity, but they are not so common as systems. The most common MIMO systems that we have found many applications, also commercial applications like the automotive radars, are the collocated MIMO systems. And we have seen that we can transmit orthogonal waveforms. In this way, the beam pattern on transmit is flat, so we don't have any, any gain in a spatial integration. But we can build the beam pattern that we want on receive. It means that we should be able to have, we should be able to perform digital beamforming, and each element of the antenna should have its own waveform generator, because theoretically each waveform is different for each antenna or receive. and then also have a power amplifier on each receiver, on each element, on transmit and on receive. So the MIMO system is generally much more complex than the usual phased array. But we have seen that the number of degrees of freedom is much higher, and then we can locate with good accuracy a larger number of targets, okay? And then this is one of the other advantage. We don't have gain on transmit, so the MIMO system can be considered a low probability of intercept radar. This is a pro, but it's also a con, because in this way we don't have gain on transmit. So on transmit we don't have a very large signal to noise ratio, but we can stay on the target a longer time. So we can increase the time on target. This way we increase the signal to noise ratio, we increase the frequency resolution, but we know that, of course, since we have many samples, it's more complex, okay, to build the system. And I think that for today, that's it. These are the references. You see that these are the first actually paper on MIMO summarizing the characteristics of the MIMO with the collocated antennas, dates back to 2007. It's written by John Lee and Peter Stoica. It's MIMO radar with collocated antennas. It's a very famous article with huge number of citations. And if you want to see the models for the signals, you can look at the papers by Friedlander on signal models for MIMO radars. Since then, there are also other papers and also books, and you can find summarizing an easy chapter also in the principle or modern radars, advanced techniques, that I think is the volume number 3. And the book, the chapter is written by Davis, okay? So you can find hundreds of papers on MIMO, because MIMO radars are relatively new as a system. So you've seen the first papers appeared less than 20 years ago. I mean, 20 years is a long time, but for radars is reasonable. There are MIMO radars already implemented, but the most common ones, as we have seen, are in the applications, automotive application. Here we can find also some other paper. The last one is on the ambiguity function. And what I find quite interesting is the second paper on Hassanian and Borobiov on the mixture of phased and MIMO radar. So practically you build a MIMO radar where instead of having a single antenna element, for instead of a single antenna, you have a phased radar. So multiple antennas that transmit the same waveform. So we have multiple groups of antennas. Each group transmits a different waveform. So each group works as a phased array, but overall the system is a MIMO system. Okay, so it's quite interesting because it's a different configuration and a different application. Okay, so I think that with that I finished. Is there any question on this topic? If there is no any question, as usual, if you have some curiosity or something, then you can write to me and I'll try to reply. Then I will share with you the slides, the updated version of the slides on passive radars, and also these slides on MIMO radars. And then we can close the lecture, and we will meet tomorrow at the same time. Okay. See you tomorrow. Bye.
Okay, ma'am. Thank you.
Thank you, ma'am.
Thank you, madam. Have a nice day.
Thank you, ma'am.
Shall I close the meeting now? Hello, everyone.
Yes,
Shall we close the session now?
yes, you can. I think madam already left the meeting.
Bye bye. Take care,
And
everyone.
and by the way, having a WhatsApp group will
Yeah, I
allow
will
us
ask
to
to sir.
interact with these
I will let you know.
other cohort members.
Yeah, I will let you know after discussing with sir.
Okay, Himanshu. Thank
Okay,
you.
bye bye, everyone. Take care.
Thank you. Thank you. Have a nice day.
Thank you.